have a few things for you to ponder. First, there are 92 stable elements on the periodic table. If that is true, how come we have billions and billions of different substances? And the answer is chemical bonding. We make compounds. Think of the amount of material that has to go into a shoe. We have steel beams, which is an alloy. Yeah, all of biology compounds. Water, the ocean, everything in the ocean. Billions of different compounds. Now, these bonds are interesting. When elements bond together, they make a new substance with different physical and chemical properties. Here's the example. Sodium, when you put it in water, explodes. Chlorine, when you just have regular chlorine, it's dangerous. It can kill you. But when we put them together and make NaCl, well, that's necessary for life. So we have two substances that could kill us, making one substance that's necessary. So we get completely different properties by bonding. There are three types of bonds: metallic, ionic, and covalent. Metallic bonds are created when a metal and another metal are put together. Also, and this is the interesting part, if it's just the single metal. So, for example, if I say iron, I don't mean one iron atom, unless that's what I'm talking about. If I say go get some iron from the back stock room, I mean iron bonded to iron bonded to iron. So the bonding in metallic elements is very, very interesting. Now, another type of bonding is ionic bonding. You're probably familiar with this. This is when a cation and an anion bond. Now, there's a couple different ways this can happen. You can have a metal and a nonmetal bonding together. You can have a polyatomic ion and a nonmetal bonding together. Or, I have to go over here now, you can have a metal and a polyatomic ion. So, a lot of different ways to form an ionic bond. Covalent bonds are formed by two nonmetals bonding. Covalents make up a large amount of what's around us. You get a couple of different choices. I call this like a simple covalent, so like CH4, sugar, things like that. There's also giant covalents, which is actually maybe better called network, but that's like sand. And then there are polymers. So each type of bonding has different things and interesting pieces about it. There are rules to do with bonding. First, there's the octet rule. Atoms will gain or lose or share electrons to have an octet on its outermost energy level. And there's an exception if they lose electrons that go back down to the 1s. Of course, it can only have 2 electrons. So if we look over here, lithium did have an electron out here on the second energy level, gave it to fluorine. So this is the first, the n equals 1. It's got a full outer layer. So the octet rule is usual. Just be aware that if it goes down to the first energy level, we're only looking at 2 electrons. Notice, however, fluorine has 8. Lithium is a plus, fluorine is a minus at this point. When a metal and a nonmetal come together, you get ionic bonds. Of course, insert polyatomic for the metal or the nonmetal, depending on the charge, and you get all the different iterations we can get. But what's interesting is we call these formula units because of the way they form together. They actually form in crystal lattices, so very tightly packed crystals, and so we can't exactly say N 10 billion, Cl 10 billion, so we come down to the lowest possible ratio. Third, when two nonmetals get together, you have a covalent bond. We call these molecules and molecular formulas rather than formula units. In this chapter, we'll look at Lewis structures, and the next chapter we'll look at VSEPR structures and IMFs. Covalents take up a lot of space. And I mean space like academically, things we've got to do with them. Number 4, you get some metals together. You'll get the elemental, the iron, as I discussed earlier, or alloys. They form crystal lattices. Their crystal lattice is just a little bit different, and their bonding is interesting. If you look over here, what happens is you get a sea of electrons. It's very interesting. Whereas covalent, you get sharing. And of course, in ionic, you get the exchange of electrons. Okay, and we call this the sea. And I'll explain this more, obviously. Now, we're going to be using some of our periodic trends to help us explain bonding. Electronegativity differences are going to be used to help us describe covalent bonds. So covalent bonds are better described using electronegativity differences. If your covalent bond has equally shared electrons, you're going to have an electronegativity difference between 0 and 0.2. And I will tell you, this is one of those ish moments, 2-ish, 0.2-ish, because sometimes 0.3, sometimes 0.4 even, you can find on scales. The big important piece here is that it is a low difference, and electrons are shared equally. If you're between 0.2 and 2 on the electronegativity difference, you're a polar covalent bond. So we've got covalent bonds, then we have different types of covalent bonds, polar and nonpolar, and of course we have the different covalent compounds we saw earlier. And then also, electronegativity can tell us a little bit about the ionic bond. The problem is, we know that an ionic bond is a metal and a nonmetal, so we don't even need to refer to the electronegativity differences. And we'll get into that. We're going to use atomic radius to help us look at alloys. Notice here, when you have a small atomic radius, you form an interstitial alloy. If your atomic radius is roughly the same size as the other atoms, you form a substitutional alloy. We will be using ionization energy and electron affinity to help us look at, looks like, ionic bonding, a cation and an anion. So all that stuff from the previous unit is important. Now let's look at physical properties of the different types of bonds. So ionically bonded substances are crystalline solids at room temperature. What that means is there is a regular repeating pattern. So you get plus, minus, plus, minus, minus, plus, minus, plus, and it forms beautiful patterns over and over again. These patterns, however, make it rigid and brittle. If you look here, we've got anions and cations. If you apply a stress, like put a hammer to it, it cleaves right off. And this is actually a very smooth point. And smooth meaning, could mean actually very, very sharp as well. And we'll look at that in real life. They also have very high melting points. If any of you cook, you know that you cannot melt salt on the stove, but you can melt sugar. Salt is an ionic compound. It's not going to melt on the stove. The reason the melting point is so high is that regular pattern of ions lock everything into place, and it takes a lot of energy to make those more fluid in nature. A large percentage of ionic compounds are soluble in water, but there are some that are not. So just be aware of that. We'll look at this later in the year with solubility rules. If it dissolves in water, it will conduct electricity in that water. So as an aqueous solution, it will conduct electricity, and we call that an electrolyte. And that's the same electrolyte that's in Gatorade. Gatorade, Powerade, all of those have salts, ionic compounds dissolved in water. And so you can see here a non-electrolyte will not light up a light bulb. A weak electrolyte will sort of light it up, but a strong electrolyte, like NaCl, will light up the light bulb. Now, they also conduct electricity as a liquid. Dissolving in water and being a liquid are two different things. When you dissolve NaCl in water, it breaks apart into NAs and Cl minuses, Na pluses and Cl minuses, and it just floats around like that. It's also in water. That's the key difference. NaCl liquid is just NAs and Cls, Na pluses and Cl minuses, floating around each other. Big, big difference. Ionic compounds will not conduct electricity as a solid. So let's look at what it looks like to dissolve in water as an ionic compound. So here you have that crystal lattice we talked about, the positives and negatives alternating and being in very, very close contact. When water comes along, it breaks the ions apart from each other. Water has a partial positive side. That's a lowercase delta. So you may be familiar with big delta, that means change. Its lowercase delta means partial change. So we've got a partial positive and a partial negative side, and it breaks it all apart. Please note that not all ionic compounds dissolve in water, but those that do are electrolytes. Let's look and see what that looks like when NaCl is put into water. So NaCl is coming down and it's breaking apart. So this is the big view. Notice they are no longer in contact with each other. The positives and negatives are just free floating around. If you look over here in the concentration box, the Na plus concentration and the Cl minus concentration are the same because it's a 1-to-1 ratio. We have an up-close view, if you'd like to see that, where you can actually see the water interacting with it all in another small video attached to this. Physical properties of simple, and this is very important, simple covalent compounds, like sugar over here, or CH4, or I can't even think of another one that's, because they're all just so common, NO2, CO2, H2O. Simple covalent compounds can be either solids, liquids, or gases at room temperature. Their melting point depends on the size of the molecule created. So sugar is a bigger molecule, so it's going to be solid, whereas CH4 is a small molecule and it's a gas. And here's the important part, and the intermolecular forces between molecules. So sugar is very interested in other sugar molecules, so they hang around each other. These melting points can be well below 0, like methane, or well over 100, depending on a lot of different factors, and we'll go into that. So some are water soluble, like sugar. Some are not, like fat, or even CH4. They are non-conductors and non-electrolytes. Water does not conduct electricity. Water that has salt in it does. So that whole pool warning thing about electricity is very real because it's got salts in it, all kinds of different salts, the chlorine salts, all the different stuff you put in a pool. So pool water will conduct, but it's not because of the water, it's because of the stuff in the water. Very important. Simple covalent compounds are non-conductors and non-electrolytes. So let's look and see what it looks like when covalent compounds dissolve in water. A few quick notes. not all covalent compounds dissolve. More ionic do than covalent do, honestly. If they do dissolve, they are non-electrolytes. They will not break up into ions. Let's see what that looks like. So this is sucrose. And what we have are 6 different sucrose molecules that were dumped out of the sugar thing, and they are floating around in water separately. It's all the sugar molecule. It doesn't break down into all the different pieces. Water just simply surrounds the whole molecule. We have a video that shows this up close if you want to watch that. It's about 15 seconds long, and it is somewhere around this one. Now, physical properties of polymers. These are large covalent compounds. Remember, polymers are bunches and bunches of small compounds stuck together. You can see a regular repeating pattern. Kind of, if I draw through here, kind of repeats over and over again. And then I feel like I've missed something. Got them backwards. I think I got it. May have chopped something off too soon. How about there? But you get this regular repeating pattern over and over and over again. And this is a polymer. They can be very, very, very big. You get some that are liquid, but for the most part, polymers are solid. The melting points are generally very high, but if you've ever put certain plastics in the microwave, you know that some are not. So melting points can vary depending on actually the bonds and what we call the cross linkage. Some are water soluble. It depends on the monomer base, and it also depends on how big the polymer is. Because in order to be water soluble, water has to be able to surround you. If your polymer is too big, water can't do that. Generally, they're non-conductors and non-electrolytes. The difference being you are a conductor in your solid, liquid, and gaseous phase. You're an electrolyte in your aqueous, meaning dissolved in water. However, there's a new class of polymers called conductive polymers that are showing big promise in energy production or energy transfer, solar power. So I can't say polymers don't conduct because there are some that do. Now we have giant covalent compounds. They are always solid. They always have a high melting point. They are not soluble in water. They are non-conductors and non-electrolytes except for graphene. Graphene was recently discovered within the last, I guess, maybe 10 to 20 years. Time gets by. And a Nobel Prize for chemistry was awarded for finding graphene. Graphene is an allotrope of carbon. So carbon will bond to itself many different ways. One of the ways will form charcoal. So charcoal is very nondescript, undefined. It's just a mishmash of bonding. It will also form diamonds, which are highly organized. It will also form graphene, which are sheets of highly organized carbon bonds. And then also, they call them fullerenes. And a fullerene is basically a carbon ball, just carbon bonds all the way through. So allotropes are the same element bonded to itself in different ways. From this list, diamonds and graphene are giant covalent compounds. So if we look over here to the top right, this is actually graphene. You've got a sheet of carbon rings, another sheet of carbon rings, another sheet of carbon rings. And these are long sheets of carbon rings. They're not bonded to each other. They just sit on top of each other, and they actually move past each other very, very easily. Here we have a diamond. So it's all carbon bonded to itself in very, very networked fashion. And then finally, we actually have sand, which is silicon dioxide. So the oxygens are the reds and the silicon is the black, and they're all bonded in a network fashion. These are giant covalent compounds. They're covalently bonded. They're very happy the way they are. They are very unreactive. Finally, physical properties of metallic bonding. They are crystalline, but it's a different kind of crystal. What they have is every metal will actually donate 1, 2, or 3 of its outer electrons to kind of form this, they call it a sea of electrons. So the electron right here doesn't really belong to this guy. It's kind of communal. Everyone has these electrons. Because of this, the crystalline shape is actually malleable. If you look up here, you apply a stress. What happens is these electrons just, oh, okay, we'll move with it. And it compensates for any movement, so they slide right past each other. This is how you can hammer out metals, flatten metals, get metals very, very, very thin. They're also ductile. That means they can be pulled into wires. Same thing, you can take a sheet of metal and over time pull it into thinner and thinner and thinner wires without it breaking. We do have one liquid, mercury. They have relatively high melting points. Obviously, you've got mercury. Over here, gallium will melt in someone's hand. But metals in general have high melting points. Some are very, very high, like tungsten. I think it's 2,000 something degrees Celsius. They're not soluble in water. And they are good conductors of heat and electricity, and that's because of those free electrons. They can move around, they can transfer energy, and this occurs as a solid and a liquid. So if you have liquid metal, it will conduct electricity.